Welcome to another Explainer. Today, we are basically becoming chemical cryptographers. If you've ever stared at the back of a shampoo bottle or a snack box and felt completely, utterly lost, well, you're in exactly the right place. We're going to transform what looks like a totally confusing jumble of letters into a highly logical, elegant, and readable language.
So let's kick things off with a pretty simple question. When you look at letters and numbers like NaCl or H2O, do you just see a random mashed up password, or do you see a clear, readable recipe for the universe? Because at its core, chemistry is just a language. And once you know the basic grammar, a whole new world opens up to you.
Here is our roadmap for breaking this code today. We'll start with elements versus compounds, look at the rules of naming, explore the oxygen effect, move on to decoding chemical formulae, and finish up by counting elements and atoms.
All right, Section 1, Elements versus Compounds, the alphabet of matter.
If you take a look at the oxygen particle, you'll see it's just two red spheres. It's pure, it's unmixed, and it's made of only one type of atom. That right there is an element. But then, look at carbon dioxide, water, and methane. These are compounds. They're these beautifully bonded combinations of different atoms. You can physically see the gray carbon bonded with the red oxygen, or the red oxygen holding tightly onto two white hydrogens. Think of it this way. An element is a single raw ingredient, but a compound? That's the baked cake.
Moving right along to Section 2, the rules of naming, chemical grammar. Just like English, chemistry has its own strict but honestly wonderfully consistent grammar rules. Step 1 is simple. If there's a metal involved, it's the absolute star of the show. It always takes the lead. Step 2, the non-metal follows right behind, but it gets a slight costume change. Its normal ending gets chopped off and replaced with IDE.
Let's actually see that in action. If you bond the metal sodium with the non-metal chlorine, we don't call it sodium chlorine. Notice how chlorine gets that quick costume change and becomes chloride, meaning our newly formed compound is simply called sodium chloride. And the exact same logic applies right down the line. Take the metal iron, add the non-metal sulfur, and you get iron sulfide. It's a beautifully predictable system once you know the rule.
Section 3, the oxygen effect, the plot twist.
Okay, so we just learned that zinc and sulfur make zinc sulfide, but what happens when a third element, specifically oxygen, crashes the party? Look at the formula ZnSO4. That O right there stands for oxygen. When oxygen is added into the mix of a metal and a nonmetal, that "ide" ending morphs into ate. So plain old zinc sulfide transforms into zinc sulfate. The very moment you hear ate at the end of a chemical name, your brain should immediately flag, aha, oxygen is in there. You know, once you spot this, you're going to see it literally everywhere. Sodium and sulfur mixed with oxygen. That becomes sodium sulfate. Copper, carbon, and oxygen becomes copper carbonate. The exact same goes for magnesium carbonate, sodium nitrate, and potassium nitrate. The secret's out. Whether it's the nitrates in your garden fertilizer or the carbonates in your daily antacid tablets, you now know for sure that the ate suffix is just chemistry's way of telling you oxygen is a major part of the recipe.
Section 4, Decoding chemical formulae, reading the code.
It turns out most substances actually have three distinct identities. There's the formal chemical name, like sodium chloride, the everyday name, like common salt, and then there's the specific formula, which is by far the most precise, because it reveals the exact symbols of the elements actively bonded together. And here is your master key for really code-breaking these formulas, the little number. Or, as we call it in chemistry, a subscript. It's written slightly below and to the right of an element's symbol. This number tells you the exact head count of atoms for that specific element in the particle. But wait, there is a vital catch here. If there is no number written next to a symbol, it doesn't mean 0. It just means 1. Scientists are all about efficiency, so they honestly just don't bother writing the number 1. Let's apply that rule right now. CO2? Well, there's no number next to the C, which means we have exactly one carbon atom bonded to two oxygen atoms, carbon dioxide. Now look at H2S. The 2 is grouped with the hydrogen, and the sulfur has no number, meaning 2 hydrogen and 1 sulfur atom. And finally, check out calcium carbonate, CaCO3. That is a molecular party of 1 calcium, 1 carbon, and 3 oxygens. You are literally reading the molecular blueprints right now.
And that brings us to Section 5, Counting Elements and Atoms, the master codebreaker.
Okay,
Let's take a look at some frankly massive chemical formulas. Things like sulfuric acid and acetic acid, H2SO4 and CH3COOH. Now, these might look like absolute gibberish at first glance, but guess what? We now have the exact tools we need to systematically break them down.
So let's tackle the biggest beast of them all, acetic acid. You probably know it as the main ingredient in household vinegar. The formula is CH3COOH. First question, how many unique elements are in there? Just look for the distinct capital letters. Second question, how many total atoms? For that, we just have to add up those little subscripts. And, crucially, remember to count the invisible ones attached to the letters without numbers.
Look at how beautifully logical the revealed answers are here. Let's trace the exact logic for that acetic acid. The distinct capital letters are C, H, and O, carbon, hydrogen, and oxygen. That makes 3 unique elements. For the total atoms, we just add the subscripts straight across the formula. 1 carbon, 3 hydrogens, another carbon, 2 single oxygens, and 1 final hydrogen. That's a total of 8 atoms tightly bonded together. Look at sulfuric acid right above it, H2SO4. Hydrogen, sulfur, oxygen means 3 elements. 2 hydrogens plus 1 sulfur plus 4 oxygens equals 7 total atoms. You've just mathematically decoded the structure of matter.
And just like that, you've officially graduated from seeing random passwords to reading the fundamental language of chemistry. The ides, the eights, the invisible ones, and the little subscripts, they all make perfect sense now. So the next time you pick up a bottle with a complex label in your pantry, don't just ignore it. Ask yourself, what secret chemical codes are waiting to be cracked inside your very own home?